Hello students, welcome to the part 2 for the preparation of amines. Now let us do the fourth preparation methods of amines. That is ammonolysis of alkyl halides. Okay, ammonolysis, the process of cleavage of carbon to halogen bond by ammonia molecule is known as ammonolysis. Therefore, ammonolysis of alkyl halides. Alkyl halides are also known as haloalkanes. Alkanes, the breakage of this bond, the cleavage of the carbon to halogen bond by ammonia molecule is known as ammonolysis. Therefore, now let us do the reaction. Now we have ammonolysis. Let us take an alkyl halide here plus ammonia. Now this ammonia, it has lone pairs. It donates the lone pair cause and attacks here the halogen atom leaves, and then we know that the halogen atoms are good leaving groups. Therefore, now we will get a resulting R and H2. Let's write here one more hydrogen, the 3 hydrogen molecules, H2 plus 1 hydrogen, and then negative because it leaves along with the bonding electrons, and nitrogen will become positive. Now, if we take a base here, this is negative, the negative and positive there attract each other. Therefore, now we have here the OH molecule goes and takes up this hydrogen molecule, and there is removal of water molecule. Now, therefore, now this hydrogen, the bonding electron pair goes and attacks the nitrogen atom, and then the halogen atom leaves along with sodium atom. Therefore, there will be NaX along with the removal of water. Therefore, we would get R and H2, our primary amine. Thus, this is the ammonolysis of alkyl halides. There, ammonolysis has one very big disadvantage of yielding a mixture of all the amines, that is primary, secondary, and tertiary amines, and also quaternary ammonium salts. However, it is noted that primary amine is obtained only when as a major product. The primary amine is obtained as a major product only when we take large excess of ammonia. Only when ammonia is taken in large excess of ammonia, primary amine is obtained as the major product. But when there is excess of both the alkyl halides and ammonia, there is a mixture of all the amines. Therefore, now let us do an example here. Now, if another alkyl halide molecule is here, the lone pair nitrogen attacks the alkyl halide, halogen molecule leaves, the same reaction that occurs in the first step. Now, here R and H, and then R will come and join here. X minus would be here, and then nitrogen would be positive. Now the same step as it is here. The OH minus goes and takes up this one. This goes away, and X leaves along with Na. Therefore, there will be removal of water, and then NaX. Then we would be getting R and H. This is our secondary amine. Nitrogen gets its lone pair. Now again, if we apply the same step, another RX molecule with NaOH, and then this is positive, therefore this one negative. Then if we this OH will take up the hydrogen molecule, this molecule, and then it will leave as water, and then there are removal of NaX. Therefore, we would get R tertiary amine, R and R. Therefore, this is our tertiary amine. Therefore, we should remember that when large excess of both the alkyl halides and ammonia is used, we get a mixture of the primary, secondary, and tertiary amines. But only when excess of ammonia is used, primary amine is obtained as the major product. Now let us do the fifth preparation methods of amines, that is the Gabriel Telemite synthesis. Okay, Telemite is also a derivative of carboxylic acid. Therefore, first let us check from where we get Telemite. Now Telemite we get, this is COOH, COO. This is talic acid. Talic acid on ammonolysis. Okay, when talic acid is ammonolyzed, we will be getting here Telemite. This is known as LAMITE, Telemite. Talic acid on ammonolysis gives Telemite, and then when we heat this, there is removal of ammonia molecule, and then we will be getting here our Telemite. Okay, the difference here is this is Telemite, AMIDE, and this is imide, Telemite. Now talic acid, Telemite is obtained from the ammonolysis of talic acid to give Telemite, and Telemite on heating there's removal of ammonia molecule, and then we get the Telemite. Now this reaction can be studied as, now the reaction is Telemite, Telemite in basic medium. Okay, in basic medium, either use KOH or NaOH. It is the same because the main medium here is OH. The second step is RX, and then addition of the alkyl halides, and then the third is hydrolysis. Now the second step is the main step. It's the main step in the Gabriel Telemite synthesis to get our amines. Okay. Now, firstly, before going into the mechanism of this synthesis, please remember that this synthesis, Gabriel Telemite synthesis, can only be used for the preparation of primary alkyl amines. Only primary alkyl amines is produced. Okay. Again, in the second step, there is reaction of SN reaction, SN nucleophilic reaction takes place, SN nucleophilic reaction takes place. Therefore, the second step is the main step in this synthesis, and remember that Gabriel Telemite synthesis is only used for the preparation of primary amines. Aryl amines cannot be produced by this synthesis because aryl amines do not undergo nucleophilic substitution, that is, SN substitution reaction do not take place in aryl amines, as we have discussed in haloalkanes and haloarenes. Therefore, Gabriel Telemite synthesis is used only for the preparation of primary amines. Now let us go to the mechanism of this synthesis. Okay, now let us do the mechanism. Now mechanism, we have here our Telemite. This is our Telemite, nitrogen with the lone pairs, KOH. Now this OH minus takes this hydrogen, and then the bond pairs goes and adds up to nitrogen atom. There is removal of water molecule, and now we will be getting here nitrogen would become negative, and then our potassium would come and add up here. Now we have here our, this is the main step comes now, alkyl halides. Now alkyl halides, we know that the halogen atom is more electronegative than the alkyl group, therefore, and halogen atom being a good alkyl halide, therefore it become negative, partially positive. Now the negative charge on now comes and attack the alkyl group, and then this potassium leaves along with halogens. Now we know that halogens are good living groups, therefore the potassium leaves along with halogens, and we would get here okay. Now here one more important step comes here. Now another more. Now when this negative charge comes and attack, now here since there is no acidic hydrogen in this substrate, the OH molecule acts as a nucleophile and then attacks the carbon atom. Now since carbon is already tetravalent, it cannot form five bonds, therefore this bonding electron goes and adds up to this oxygen. However, their back bonding occurs in oxygen atom, therefore again this oxygen back bonding, there is back bonding, the back bonding occurs, and one more bond breaks up again, and then the bond breaks up, one more bond breaks up, this again bond goes back to this oxygen atom, therefore one more bond breaks up, therefore this bond breaks up and then goes to hydrogen and goes to the nitrogen atom. Nitrogen attacks the two bonding pairs. The two bonding electron pairs as nitrogen is more electronegative than carbon atom, therefore the bond breaks here. Now we would get our resulting product would be see our CO would be here because the bond was not broken. OH came and attached to the carbon atom, therefore OH, and then we have here our N. Our N took away both the bonding electron pairs, therefore it would become negative. Now there is proton transfer. Proton transfer takes place. Sorry, this should be only hydrogen. Proton transfer takes place, therefore the hydrogen atom goes here. There is transfer of proton, and there is transfer of proton, and then therefore the hydrogen atom goes and goes and pairs up with the nitrogen atom, and then we get here see. Okay, before giving the product, we know that by resonance CO minus is more stable than the carboxylic acid COOH. Therefore, the transfer of the proton, since this CO minus wants to become more stable than COOH, therefore there's the transfer of the proton takes place. Therefore, we would be getting here COO minus more stable than COOH. The K plus will come here. The K plus from here, and then NHR. Now, so that is the product. Now again one more K plus OH minus. Now this OH minus acting as nucleophile goes and attacks the carbon atom. The same reaction that occurred here will occur here. Since carbon cannot form 5 bonds, therefore one bond, it breaks one bond and goes away. But again oxygen atom, there's back bonding, and oxygen atom back bonding occurs, and then the oxygen atom gives its electron pairs. However, now there one more bonds break up, and then this bond goes to nitrogen atom. Therefore, we would be getting here, this will remain as it is, and then here COO was here, and then the OH came and joined here, and then we had our product N plus RNH nitrogen. The bonding electron pair came and bonded to nitrogen, therefore nitrogen would have here one negative charge. Now from here again proton transfer takes place. Again, the proton transfer takes place. The hydrogen atom, there's proton transfer. Hydrogen atom goes and bonds with nitrogen atom, and then this bond along with it bonding pair goes to the oxygen atom, and therefore we would be getting our resulting amines, that is RNH2 plus the acid C minus K plus. Therefore, this is the mechanism for capryl Telemite synthesis of amines. Please note that in capryl Telemite synthesis, only primary amines are produced. Aryl amines cannot be produced because aryl amines do not go as a nucleophilic substitution reaction. Okay, now the last preparation methods of amines, that is Hofmann-Bromamide degradation reaction. Hofmann-Bromamide degradation, this reaction is preparation of primary amines by treating amide with bromine in aqueous or ethanolic solution of sodium hydroxide. Okay, in this reaction, bromine is used and amide is used. Now we have here amide. Let's take an example here. Amides, we know, as discussed in the first few preparations, that amides are the derivatives of carboxylic acids plus bromine in a basic medium. Basic medium, we would get our amines plus sodium carbonate plus NaBr plus H2O. Now, please remember that in this Hofmann-Bromamide degradation reaction, only one unit of the bromine molecule is used, and then this will be, I will explain this in the mechanism. And then this Hofmann-Bromamide degradation, the word degradation here means there is degradation, one carbon atom less here. The primary amine form is one carbon less than the starting molecule. In the starting molecule amide, there was one carbon more, but this COO molecule was removed to get these two. Therefore, the resulting product is one carbon less than the starting molecule. Therefore, this is known as the degradation reaction using bromine and amide reaction. Now, let us do the mechanism. Okay, now our mechanism. These are amide. The base X first. Now this OH minus takes up this hydrogen molecule. The bonding electron pairs goes to nitrogen atom. Therefore, there is removal of water molecule. There we would get here RCON negative and then H. Now we have here our bromine molecule. Now, because of the presence of the negative charge on nitrogen atom, the dipole in bromine molecule is induced. Therefore, this is partially negative and partially positive. Therefore, nitrogen atom just goes up and attacks here, and then the bond, along with the bonding electron pair, another one more unit leaves, that is Br minus molecule leaves. Therefore, our resulting substrate with NH and then Br, we will be getting here Br. Now the second unit of NaOH minus plus. Now this OH minus, so let us write this hydrogen like this. Now OH minus takes up this hydrogen, the bonding pair coordinates up to hydrogen, there is removal of water. Therefore, we would be getting here RC double bond 0 oxygen, and then NBr, nitrogen being partially positive. Now the next step, from this step it is known as the rate determining step, or RDS. This is known as the rate determining step, and this is a very important step in this reaction. Now in this reaction, okay, the negative charge on nitrogen comes and attacks here. Now since carbon atom cannot form 5 bonds, automatically the bonding pair goes up to this. Now there's back bonding occurs again, so the bonding pairs, the electron comes again. Now therefore there is breakage of one bond, and the alkyl group, R group leaves. The R group leaves. Therefore we would be getting here. Now let us write here OC double bond N, and then BR. R has already left us, and it is here along with the bonding electron pair. It has left along with the bonding electron pair. Now this bonding R minus goes and to this nitrogen atom, and then the bromine along with the bonding electron pair leaves. Now therefore we would be getting here double bond C, double bond N, R. Now hydrolysis takes place. Now let us write here the water molecule. Now water molecule donates its bonding electron pairs, donate its electrons to carbon atom, more like partially electropositive, and then therefore this bond goes and adds up to nitrogen. O double bond C, water molecule is here. Oxygen has already donated its electron, therefore it will become positive, and then N, R, nitrogen will become negative because excess of electron has been added to nitrogen atom. Now there hydrogen atom, the hydrogen atom leaves as a proton and then bonds to nitrogen atom, and then this bonding electron goes and adds up to oxygen molecule to fulfill oxygen C. We have NH and R, and then we would be having here one hydrogen molecule has left as a proton, therefore we would be remaining of only O and OH. Now we have to remove carbon dioxide molecule, and then this removal of carbon dioxide molecule is stabilized, thermodynamically stabilized by entropy. Therefore now this OH minus comes and adds up to this